Let lambda be a Riemann surface lamination with all leaves conformally hyperbolic. Every leaf has a unique hyperbolic metric in its conformal class. So we can find a real valued function f so that the metric g times e to the f is leafwise hyperbolic. Candel's theorem says that the function f is continuous on lambda. What this means is that if lambda has all leaves of hyperbolic type, then it admits a metric continuous in lambda and leafwise isometric to a quotient of the hyperbolic plane. Candel's theorem is really a theorem about monotonicity of the hyperbolic metric as a function of the domain. This is usually expressed as the Schwarz Lemma. Schwartz Lemma says the following: let f be a map from the unit disk to itself, which is holomorphic and takes 0 to 0. Then the norm of the derivative at 0 is less than or equal to 1, with equality if and only if the map f is simply rotation through some angle theta. Here's the proof. The holomorphic function f takes 0 to 0. Another way of saying that is that f has a 0 at 0. So we can form a new holomorphic function, g of z equal to f of z divided by z, defined a priori on the punctured disk, but which extends holomorphically over the entire disk because it's bounded near 0. Now, the norm of g is less than or equal to 1 on the boundary, because the same is true of f. So by the maximum principle, the norm of g at 0 is less than or equal to 1, with equality if and only if the norm of g is identically equal to 1 everywhere, in which case g is a constant equal to e to the I theta for some theta. But g at 0 is equal to the derivative of f at 0, and therefore the Schwartz Lemma is proved. This has the following corollary. Let U be a subset of the unit disk D, and let U be simply connected. We can compare the hyperbolic metrics dSU on U and dSD on D. Then, for a vector V contained in U, the norm of V in the hyperbolic metric on U is greater than or equal to the norm of V in the hyperbolic metric on D, with equality for some non-zero vector if and only if U is equal to the disk D. Another way of stating this more informally is that vectors as measured in U are longer than that as measured in D, or the inclusion of U into D is 1 Lipschitz with respect to their hyperbolic metrics. Here's the proof. After composing with the Mobius transformation of D, which preserves the hyperbolic metric on D, we may assume that our vector V is at the origin, so that 0 is a point in U. Let's let f from D to U be an isomorphism taking 0 to 0. Then the pullback of the hyperbolic metric on U is, by definition, the hyperbolic metric on D. Now apply the Schwartz Lemma. Say that a map phi from the unit disk D to lambda is holomorphic if it maps D into some leaf lambda holomorphically. The set of holomorphic maps is topologized as follows. We can think of it as a subset of the space of all continuous maps from the unit disk to lambda, which has the compact open topology. Then we give the set of holomorphic maps from D to lambda the subspace topology. In this topology, we have the following lemma. Suppose phi sub I is a sequence of holomorphic maps from the unit disk D to the lamination lambda. And suppose this sequence converges as a sequence of continuous maps to some continuous map phi from the unit disk to lambda, then phi is holomorphic. In other words, it takes the unit disk into some leaf, and as a map from the unit disk to that leaf considered as a Riemann surface, it is a holomorphic map. The proof of this is immediate if one works in local product charts, where it simply becomes an observation about continuous limits of families of holomorphic functions. We are now in a position to prove the following key compactness result. Let lambda be a compact Riemann surface lamination with all leaves conformally hyperbolic. Then the space of holomorphic maps from the unit disk to lambda is compact. Let's begin the proof. Give lambda a leafwise Riemannian metric in its conformal class. The lemma we just proved shows that a continuous limit of a sequence of holomorphic maps is holomorphic. So it suffices to show that the family of all holomorphic maps from the unit disk to lambda are equicontinuous, where D has the hyperbolic metric. We prove this by proving the contrapositive. We show that for a compact Riemann surface lamination, if there is a sequence of holomorphic maps whose derivative blows up somewhere, in other words, if the set of holomorphic maps is not equicontinuous, then we can actually find a non-constant holomorphic map from the complex plane into lambda. Such a map shows that at least one of the leaves of lambda is not conformally hyperbolic. This will prove the proposition. Let's prove the claim. We have a sequence of holomorphic maps Fi from the unit disk to lambda which blow up somewhere. After precomposing with Mobius transformations, we can assume that the derivatives blow up at the origin. In other words, the derivative of Fi at 0 goes to infinity as I goes to infinity. Let's let Ri be the norm of the derivative of Fi at 0. And suppose that Ri goes to infinity as I goes to infinity. The disk of radius Ri maps to the unit disk by a dilation, simply multiplication by 1 over Ri. Composing with Fi gives a map from the disk of radius Ri to lambda, whose norm at 0 is 1. If we could control the norms of these maps on the rest of the disks, we would get a family of equicontinuous maps which converged in the limit to a holomorphic map from the complex line into lambda. The trick, therefore, is to find a new sequence of maps G sub I from the unit disk to lambda, where the norm of Gi at 0 is equal to Ri going to infinity, and where the supremum of the norm of the derivative of Gi over the entire disk is realized at the origin. If we knew that the norm of the derivative of Fi was bounded on the entire disk, we could simply find a place where it attained a maximum, or close to the maximum, and precompose with a Mobius transformation so that the maximum was realized at 0. The trouble is, a priori, the derivative might go off to infinity as we head out to the boundary of the non-compact unit disk. Here's how we remedy this. First, take a map from the unit disk to itself, which is multiplication by a number very, very close to 1, say 0.999. The composition of this map with Fi has derivative which goes to 0 as we head out towards the boundary of the unit disk, and therefore the maximum norm of the derivative is achieved somewhere in the interior. That maximum is very, very close to R sub I. After precomposing with a Mobius transformation, we can assume the maximum is realized at 0, and then apply Fi. We get a new map from the unit disk to lambda, whose derivative at 0 is very close to the number Ri, and whose derivative has maximum at the origin. This completes the proof of the claim, and therefore also the proposition. Now let's begin the proof of Candel's theorem. Leafwise uniformization multiplies distances by some factor e to the f. We want to show that the function f is continuous. Here's how we compute the function f. Given a point P contained in a leaf, little lambda, we look at the universal cover, lambda twiddle of lambda, and a lift, p twiddle of P, and look at a map phi from the unit disk to lambda twiddle, taking 0 to p twiddle. Then the derivative of phi at 0 has norm equal to e to the minus f. First, we show that the function f is lower semicontinuous. Pick a point P contained in a leaf lambda. Let's let phi be a map from the unit disk which uniformizes a very big ball in lambda twiddle, the universal cover of lambda, centered at the point p twiddle, a lift of P. If the ball is big enough, the norm of phi at 0 is very close to e to the minus f at P. On the other hand, the image of phi is contained in a compact subset of lambda twiddle, and since leaves of a lamination vary continuously on compact subsets, for every nearby point p prime contained in a leaf lambda prime, we can find a nearby map phi prime from the unit disk to lambda prime, taking 0 to p prime, and for which the norm of the derivative of phi prime at 0 is very close to the norm of the derivative of phi at 0. We can use the Schwartz Lemma to compare the map phi prime to the uniformizing map for the universal cover of the leaf lambda prime, and deduce that e to the minus f at p prime is greater than or equal to the norm of the derivative of phi prime at 0, which is very close to the norm of the derivative of phi at 0, which is very close to e to the minus f of p. Therefore, e to the minus f of p can only go down in a limit. Now let's prove that f is upper semicontinuous. Let pi contained in leaves lambda I converge to the point P contained in lambda. For each I, let's let phi sub I be the map from the unit disk to lambda I, which uniformizes the universal cover, composed with projection from the universal cover to lambda I, and takes 0 to the point P sub I. This gives us a family of maps from the unit disk to lambda. By compactness of the space of holomorphic maps, true because lambda has all leaves of hyperbolic type, the sequence phi sub I has a subsequence that converges to some map phi from the unit disk to lambda, taking 0 to the point P. Now, the limit as I goes to infinity of e to the minus f at p sub I is equal to the limit as I goes to infinity of the norm of the derivative of phi sub I at 0, which is equal to the norm of the derivative of phi at 0. But by the Schwarz Lemma, this is less than or equal to e to the minus f of p, and therefore e to the minus f can only go up in a limit. This proves that f is upper semicontinuous, since it's also lower semicontinuous it must actually be continuous, and therefore Candel's theorem is proved.